So the third device, we have pipe orifice. So it is a similar effect with ventrilometer that can be achieved by inserting an orifice plate which has opening in it smaller than the internal diameter of the pipelines. So this is the pipelines. Okay, so then we insert a small orifice at the A2 here, and it will give the smaller effect. Okay, constriction of the velocity of the flow in the pipelines. Okay, so the orifice plate produce constriction of the flow at A2. So this is the orifice, so this is the A2. Okay, so automatically when we have the difference area, so it will give the difference velocity. Okay, so this is A2 and the V2 happen at the A2. Okay, so this is the area 1, so this is the velocity 1. And then the flow immediately downstream of the plate will be same as the orifice. Okay, so Q equal to AV, so diameter of the orifice may cause the changes of the velocity. And then cheaper than velocity meter, but there are substantial energy loss. So velocity theory equal to ventrilometer, and then the flow rate actual is 2/3 of this value of the real value, and it may have the CD, that is the coefficient for the sharp edge orifice, that is the value of 0.65. So next we have small orifice. Orifice is an opening, basically circular, in the side or base of the tank or reservoir. So we have this, for example, it is a tank or reservoir, and then we have an opening, like a circular opening here. Okay, and then this water has been discharged in the form of jet. In the form of jet means it is shooting out to this from this reservoir or tank. Okay, and then this water basically will discharge into the atmosphere, meaning it is open. Okay, it does not discharge into the pipeline, but it is discharged to the atmosphere. And then the volume of flow rate depends on the head of the fluid above the level of an orifice. So volume of the flow rate that is charged is the same, depends on the head of the fluid above the orifice. Therefore, the small orifice has diameter or vertical dimension smaller compared to the head producing flow. Hence, the head does not vary much, but from point to point across the orifice. Referring to this figure, at point A here, on the free surface, the pressure is atmospheric. If the tank is large, so the velocity is negligible. So as we know, when the fluid is exposed to the atmosphere, the pressure is 0, and also the velocity and in this tank is almost negligible. So we assume there is no movement of the fluid of the flow inside this tank. Okay, at point B in the jet, just outside of the orifice, so the pressure at the point B again will be atmospheric. Okay, because it's shooting out, it's discharged out from this tank to the atmosphere, but the velocity is equal to V, the jet velocity. Okay, although it being discharged to the atmosphere, so the P is atmospheric. However, since it is flowing, there are flowing of the fluid, so we have the discharge, we have the velocity. Okay, that going out from this tank through this orifice opening. Okay, so the velocity may same with the jet velocity. Okay, that is the difference between the velocity that exposed to the atmosphere at the surface of the tank and velocity that discharged to the atmosphere from the orifice opening. So the taking datum at the center of orifice and applying the Bernoulli equation to A and B and assuming there is no loss of energy. So by having this height of area height of point A, head loss at point A equal to head loss at point B, so we have the ZA minus ZB is H. So we have the velocity at A that exposed to the velocity at A at the surface of the tank, okay, and exposed to atmosphere is 0 because we assume that the molecule is steady. There is no movement of the molecule at the surface of the tank, so it is 0. And then the velocity at the orifice opening that project out through the orifice, okay, from the orifice opening, okay, so we have the velocity BB equal to V, okay, and then the pressure at the surface of the tank equal to pressure at the orifice opening, PA equal to PB. So therefore the velocity theory can be calculated by using the square root of 2GH. Therefore flow rate theory equal to QAV, QA times V, velocity theory. And then the flow rate of the actual equal to the coefficient of discharge times with the flow rate of theory. So we just put a CD here times A square root of 2GH. So actual velocity, that is the velocity of jet, will be less than the velocity theory because of energy loss between A and B. Therefore, the actual velocity at B equal to the coefficient of V times velocity theory, so CV times with the 2 square root of 2GH, and then the jet area B is less than the area of the orifice A at C, and then the pressure at C is greater than the atmospheric pressure. Okay, so the section through is called the vena contracta. Therefore, actual area at B equal to coefficient of the contracta CC, okay, times with the area. So actual flow rate is CC times A times with the CV times with the square root of 2GH. Alright, so by comparing the coefficient of discharge equal to CC times CV, so we have these three formula. Coefficient of discharge equal to flow rate actual over flow rate theory, and then we have coefficient of constriction, yeah, equal to area of jet over area of the atmosphere, and then CV is the coefficient for the velocity equal to velocity jet over the velocity theory. Okay, so this is the coefficient for each symbol for each of the coefficient CD, CC and CV. So the theory of small orifice can be extended to calculate the times required to empty a tank. So we can use the time equal to 2A times H1 power of 0.5 minus H2 power of 0.5 over the flow rate, the coefficient of discharge times with the area square root of 2G. So now let's look into this example. So we have a sharp edge orifice 4 cm. So this is the orifice of 4 cm in a diameter at the base of the storage tank. So this is the storage tank, and then it discharges water under the head of 6 meter. So the tank level is at 6 meter depth, and then if the CV, the discharge of the velocity is coefficient of the velocity is 0.97, and this coefficient for the contractor is 0.62. So determine the diameter of the jet at the vena contracta. Okay, so how to solve this? Since it is given the diameter of orifice is 4 cm, so therefore we use to calculate the area. Okay, area of orifice, scalar orifice equal to pi d square over 4. So we get the area of orifice is 1.257 respond to negative 3 meter square. So therefore we use the formula for the coefficient of the contractor equal to the area of the jet over the area of the orifice. So now we know that area of the jet is cc, contractor, times the area of orifice. So we put the area of the orifice 1.257 times with the coefficient of the contractor 0.62. So we get the area of jet is 7.8 exponent negative 4 meter square. So now we can calculate the area of jet equal to pi d square over 4. So we can determine the diameter of the jet, that is equal to 0.0315 meter. And then by using the velocity of the jet equal to the velocity actual, that is discharge coefficient of the velocity times with the square root of 2gh. So we put the coefficient of 0.97 times with the 2gh. H is the depth, height of the in the tank, that is 6 meter. Okay, so we get velocity of the jet equal to 10.52 meter per second. So therefore, for the third question, to calculate the discharge in meter cube per second, so we use formula Q equal to CV times CC times area times 2GH. So you just put all the coefficient inside this formula and you get 0.0082 meter cube per second. Okay, so next we will move to this example in the next video. Thank you.